getting the opportunity to be there. And I would also actually like to thank the organizers of a different conference. One of them is here, Michael Falk, that had a very fancy title, From Atomic to Tectonics. It was a KATP program in 2005 in Santa Barbara. And so this is where I actually met Jay, and we shared an office for about 4 months, I think. And at the time, a quick computation will tell you that Jay was 48. And if you look at the program of the conference, you will see that he was very involved in solving the aging problem, actually. And we know that he did the year after that by stopping at 49. So besides aging, he was also very keen on discussing elasticity, plasticity, and friction. Not only because this was partly the topic of the conference, but also because he was remotely trying to understand what his PhD student was doing in Jerusalem, a PhD student named Shmuel, which I didn't know at the time. And this resulted in a nice paper that they did together later, a year later, on history, dependence, and contacts. So for this presentation, I will try to take the same ingredients, actually, and to mix them in a different order, elasticity, friction, and plasticity, and to see what comes out. And hopefully something nice will come out. It's not published yet. It's not even submitted. So let me start with the motivation of this work, which is with this theoretical work or modeling work, which is actually an experimental work done by the group of Jérôme Crassou and Axel Amont in Rennes. And so what they do is to do experiments on a granular medium, which is pressurized, so it's kind of compacted here, and it's submitted. So it's submitted to a uniaxial test or a biaxial test, if you want. And what they do is to monitor the plasticity inside this granular medium by actually looking at the speckle pattern that is reflected from the medium. And so how they see plasticity is not by looking at the speckle pattern itself, but by looking at the decorrelation of the speckle pattern. So essentially, the decorrelation of the speckle pattern gives access to the very local plastic activity near the surface of the medium, because of course it's not a transparent medium. And so this is the plastic activity. So they have a map of plastic activity in the zone that is illuminated by the laser. And then they can actually look at the correlation maps of this plastic activity. So let me first show you what they get. So this is the stress versus strain curve. So this is essentially what we have seen in Itamar's talk or previous talks, except now it's a quite macroscopic sample, so you cannot really resolve all the wiggles here. But the wiggles are resolved in space and time, actually, by looking at this decorrelation of the speckle pattern. So the dark dots here are where the speckle pattern gets decorrelated, and this is where plastic activity is taking place. So this is what you see in the first part of the loading, and this is essentially in what Itamar was showing corresponds to kind of isolated or dilute events, dilute plastic events. And so you do not see much here. Here, at large strains, you see very clearly formation of shear bands. Okay, so here you can really see things at the macroscopic level. But now, if you get more in the details and now look at the correlation inside this picture, here again you see very clearly that there is an internal structure, and so you have preferential orientations inside this picture. So now, if you look at the angle, the preferred angle theta here that emerges from the analysis of these correlations, it turns out in these experiments to be around 53 degrees. If you look at the correlations at the angle of the shear bands here, it turns out to be close to 60 degrees with variations, because there is also, I mean, the shear bands are sort of attracted by the corners of the sample, etc. And there are variations from sample to sample, but it's always around 60 degrees. So the question I would like to ask is, why these two angles are different, because you could think that the angle that prevails in the correlation between small events is the same that will be preferred by the shear bands. So in order to try to answer this question, I will use models that are very much like what Alan Nidelman was describing, which I describe as elastoplastic models of flow, and that we have been using for now a while to describe flow in disordered solids. So disordered solids can be metallic glasses, like Alan Nidelman was describing, but they could also be foams or colloids, and things are quite universal in terms of the description of the flow, even if they have very different hardnesses or length scales. So as we have seen already, if we look closely at the stress-strain curve, if we magnify it enough or take a small enough sample, we see the wiggles or fluctuations that Alan Nidelman was mentioning. And these wiggles or fluctuations that you can see in experiments as well as in simulations have been now for a number of years associated with these shear transformations. Well, some people prefer to talk about shear transformation zones. I prefer to talk about shear transformations because I do not really need to have specific zones here. And these shear transformations, as we have seen, are local mechanical instabilities of a region of the material involving maybe a few tens of particles of atoms. And these the local energy landscape of these particles is tilted under the influence of the external stress. And at some point, there is an irreversible instability within this local region. So this is what Itamar was showing, these crosses that you had here, that you maybe still have over there. Okay, and when this happens, the surroundings essentially respond as an elastic medium, homogeneous elastic medium. Okay, and so this event, accompanied by the response of the surrounding elastic medium, would be the elementary event that in the deformation of an amorphous solids. So it was already mentioned that essentially, also taking a very average view, these events can be seen as Eshelby transformations in which the local region I mentioned before and we talked about before, wants to change from some undisturbed spherical shape to an elliptical shape. As was mentioned, this is something that was worked out by Eshelby in the late 1950s. But essentially, it's not a very complicated problem. If you just are interested in what happens at long distances, the far field, then this just corresponds to this inclusion, so this shear transformation, exerting two force dipoles on the surrounding medium. And the surroundings respond as an elastic solid. And so this is the basic element that essentially Alan Nidelman or ourselves use in order to model the flow of amorphous solids, forgetting about the atomistic details and taking these at the elementary event. This is the elementary events is also well documented in experiments. So again, I do not want to go into the details, but this is an experiment in which the correlation between the plastic activities are studied in a colloidal paste, and you see this kind of quadrupolar shape that correlates between events appearing at the level of the correlations in the plastic activity map. And here you see that typically the correlations, this is in a colloidal system. Here the correlations appear to be at 45 degrees, and this corresponds to the preferred direction in the propagation or in the response of the elastic medium to such a pair of dipoles. Okay, so one can take these ingredients and build a very simplified mesoscopic model on this basis that can be implemented on a lattice or on a disordered mesh, depending on what you prefer. And this is also very close to what Alan Nidelman was showing, except that here I worked with a very simple model in which the stress is just a scalar. And essentially, one builds, in order to describe the flow of amorphous solids, a model in which each of these squares here becomes a lattice site. This lattice site has the potential to undergo a shear transformation under the influence of the external load. And when it does undergo the shear transformation, the stress is redistributed to the neighboring lattice sites. So one has here the mechanism for creating avalanches. Okay, you yield in some point. This point undergoes a plastic strain. The stress will increase on other sites or decrease, but in places it will increase, and this may trigger avalanches. So the ingredients that you need, there are several ingredients, and this was also mentioned by Alan Needleman. It's phenomenological, so you need a few ingredients. Like, for example, what is the rule here for yielding? How do you decide that this site will yield? How do you decide that this site will finish the shear transformation? So will it take some time? Will it take some finite strain, etc.? So these are rules that you can play with. It's a kind of cellular automaton. And by playing with these rules, you can reproduce different experimental phenomena. I will not tell much more about this. I would like to acknowledge that, in fact, the name of Purbeck was also mentioned by Itamar. And the first model of that kind I'm aware of was actually proposed by Chen, Bach, and Obukov in 1991. And they proposed this as a model of earthquakes. It was not very successful for various reasons, I guess. But in this paper, they very clearly describe what I described also here. So when there is a local shear transformation or shear deformation, this causes a very anisotropic redistribution of the elastic forces, falling off as 1 divided by r to the d, where d is the dimension of space. And they produced, with very small systems, some kind of Gutenberg-Richter type of flow. I'm not sure I would really trust this data nowadays, but it doesn't matter. So let me mention that this kind of mesoscopic description has been used, and we have a review that is available on arXiv if you are interested, to discuss a number of qualitative and quantitative features of the flow of amorphous solids, flow curves, flow profiles. Polar law distribution of stress drops is a very interesting topic. The conditions for shear band formations in various types of systems. The possibility of observing a special type of relaxation that is called compressed exponential in gels, creep phenomena. And so today I would like to discuss the application to granular media. So in order to discuss the application to granular media, I have to go a little bit beyond this very schematic view of a scalar stress. And let's stay in 2D for simplicity, and because the experiment is essentially 2D. So in 2D, the stress tensor is characterized by 3 coefficients. You have the pressure, you have the shear stress on the diagonal, and the off-diagonal shear stress. So if you now imagine that you make a shear transformation, and because of the geometry of the experiments, I will not here consider shear like this, but actually shear like that. Okay, so I do a shear transformation that is oriented like this, and that corresponds to an extra stress delta sigma applied here and here. Then the response of the medium can be computed in the far field, or assuming that here these are point dipoles. Okay, this is not really the Eshelby calculation, it's a very simplified version of it. So you can compute the response for the pressure outside, and this turns out to be cosine 2 theta divided by r squared. You can compute the response for the diagonal shear stress, and this is cosine 4 theta. This is this quadrupolar response. And you can also get the response for the off-diagonal stress. So, yeah.
How good is this description in light of the force change that exist in the granular medium? It's very non-isotropic.
I'm not saying it doesn't matter. I do not know. So I will be kind of totally ignoring the fact that you may question elasticity for a granular medium. I will assume my granular medium is an elastic continuum. Okay, so this is the pictorial representation of the stress redistribution, so of these fields here, delta sigma and delta p. So you see the quadrupolar shape for sigma and the dipolar one for p. So now, I will not completely ignore the fact that I have a granular medium, but I want to take it into account only in one ingredient of my model, which is the criterion for failure. And of course, no one knows exactly what is the local criterion for failure inside the granular medium. So let's assume that this is a kind of more Coulomb criterion, so that you have a local friction inside the medium. So I'm treating my discrete granular medium as something that is continuum and that has a frictional failure criterion. That is, the system will fail if the shear stress, if the local shear stress exceeds the pressure times the friction angle plus some contribution, which is the cohesion strength of the medium. Okay, so this is the more Coulomb criterion. Okay, and so the shear, it's very well known in continuum mechanics. And so from this, I can define what I call a yield function, which is just essentially the distance, the local distance I am from failure. So the difference, at any point in the material, the difference between the shear stress and the pressure times the sine of the friction angle. So now, the question I would like to ask is, if I take these two ingredients, what is the response not in the shear stress or in the pressure, but really what is the response of this yield function to a local event at the origin? Okay. Oh. Sorry. So it's not moving anymore. Okay, that's working. Okay, so this is the response, and you see that obviously, because the yield function is a combination of pressure and shear stress, then it will somehow combine the two dipolar and quadrupolar contributions to yield preferential directions that are at an angle which is neither 45 degrees nor 90 degrees. Okay, so, okay. So now what we suggest here, and I don't have a proof for that, but is that if there are strong correlations in the yield functions, this is where I should observe preferential directions in the correlation picture. So when we have these weakly interacting kind of isolated events, then I can expect that one event at the origin will preferentially trigger a new event where the change in the yield function is maximum. Okay, this seems a reasonable assumption, and so this gives us a value of the preferred angle in the correlation, which is easily computed and can be related to the local friction angle I was assuming in the Moore Coulomb law. You can actually refine the computation and get anything you want if you would like to fit the experiments by introducing the possibility of having a local dilation. So in addition to the local shear stress, you could have a local dilation that corresponds to a local increase of pressure. And then this modifies the maximum, the angle for the maximum in the yield function, in the change in the yield function. So you just have two adjustable parameters here, and you can get the angle you would like to. Okay. So now what about shear bands? Shear bands, as we have already heard, is a kind of collective plastic activity that is localized inside a region that is narrow but extended in the linear direction. Okay? So then I would like to describe the band as a linear array of shear transformations operating at the same time. Okay? And mathematically, it could be just a continuum of shear transformations. And of course, as we have seen from the picture of Itamar, which is probably still here, okay, So in this case, if you have an activity that is homogeneous on the line, then there is no stress redistribution outside. So in fact, the contribution for the different zones that are operating together cancel out when you go outside of the band. Okay. And so based on this, in principle, you could have a band in essentially any direction. So what we propose is that the criterion that will select the direction of the band is not, as usual, to say it's 45 degrees because of the shear stress, but it's actually that it maximizes the change in the yield function inside the band. Of course, if you have a band that is operating, the yield function doesn't change outside, so one has to consider what is happening inside. Okay. And so when you do the calculation, so you just create a shear band as a sum of delta functions that are regularly spaced along a line at some angle alpha. You compute the response for the pressure, for the shear stress inside, which will be 0 everywhere except along the line itself. And if you maximize the change with respect to the angle alpha here, you get that the maximum change in the yield function is obtained for a value which I call theta shear here, shear band, which is given by this formula, and which is in general different from the angle for the correlations unless phi is equal to 0. Okay, you can use this to define a macroscopic Coulomb angle, but that's not too important. So now we can try to test this numerically. And essentially, numerically, what we do is similar to what Alan Needleman was showing. We have a finite element grid. Each element represents a potential shear transformation. In each element, we have a local failure criterion with some angle. In order to get some disorder, we put the disorder in the cohesion, but it's not, I mean, you could also put it probably in the friction angle. And then what we do is to apply the shear. Then you will trigger a shear transformation, the first shear transformation when the Moore Coulomb criterion is met. Then you can solve for the displacement, and we do that with overdamped propagation, so it's rather, there is no inertia essentially. And then, of course, you will trigger new events if the local failure criterion is reached at different points. Okay? And when you do so, this is the stress strain curve. So, okay, we have a peak and then some wiggles here. In this part, we have only rather isolated events, and at the yield strain, we start seeing events that start being collective, as Itamar was showing. And the important point is that when we go along and increase the deformation, these events actually, these lines of collective events always take place in the same location in space, along the same location in space. So we have shear bands that are here, I would say, not propagating, that are quite stationary. Now we look at the prediction from the kind of theoretical calculation I showed before is that in the correlation we should have an angle for the numerical values we have here are 51 degrees and 58 for the shear bands. So for the shear bands, this works quite well. So these are the correlation patterns in the region where you have shear bands. And we see that indeed the angle is quite close to the predicted 58. You can also see here, do an angular plot of the intensity and get the 58. For the part that is before yield stress, it's the data is much more difficult to collect because you have relatively few events and little statistics. But essentially, we get that the data is more blurred. There are more possible orientations. And if we look at what it gives, we get an angle here, but I wouldn't really necessarily insist on that. That is in between 51 and 58. So presumably, it's some kind of mixture of the shear bands and the isolated events here. Okay, so that would be my conclusions, that we can use a relatively simple elastoplastic model to describe the deformation of the granular media, and that interesting stuff arises if you combine a local criteria, a local Moore Coulomb criterion, not just a von Mises criterion, with elastic redistribution. So we have interesting stuff in plasticity combining friction and elasticity. And the proposal that we are making is that the transient correlations are dominated by the response to one shear transformation, while the shear band orientations corresponds to some kind of optimal collective soft modes, but which is, in a sense, a rather nonlinear mode. It's not like okay. And numerical simulations seem to confirm this. Thank you for your attention.
Really nice recent work where he showed that that if you think of soft materials like gel or tissue, and you think of an Eshelby inclusion that has, let's say, water in it or oil in it, that Eshelby theory breaks down if you don't, because of surface tension effects. That the material, that if you're small enough, so
well, I wouldn't say that Eshelby theory breaks down, because Eshelby theory doesn't include surface tension. So
so it doesn't work. How is that?
So well,
you have a little round hole and it deforms and does everything, and I try to compare it to Eshelby theory and it doesn't work because surface tension is comparable to the elastic energies. And I found it very surprising. I mean, it's trivial, but I find it surprising. No, STZs are very small, right? There are a few atoms in these simulations. So on that scale, isn't also a question about surface energy compared to elastic energy? Can you really?
I mean, really, what one needs is not Eshelby, and we are using. If you look at Eshelby's paper, it's very. The calculations are kind of complicated, and what we need is just a claim that the local transformation corresponds to two force dipoles, and even with surface tension, I would imagine that. So here you have two force dipoles.
No, you have an elastic response.
Sorry.
You have to have an elastic.
Yeah. I mean that the medium is responding. That the medium is elastic and that it's responding to two force dipoles. Plus, potentially, you could have a local dilation as well. And in fact, Eric Wicks did some experiments on forms, and in forms, it appeared that in order to interpret his correlation data, he needed to include some dilation as well.
So it's size dependent, right? The response depends on the size of the deformed volume. That's the modification you get from the surface. So you're saying it doesn't matter for your continuum model because you assume elasticity and it's all in there.
Exactly.
This is the elastic.
It's only the first line here.
Cannot fail.
The principle isn't dependent on the size of your deformation. That's the size of your object.
So the question is sigma alpha beta what's written here or something else? That's all.
I just have a comment. I mean, Eshelby solution is a solution in linear elasticity.
Right.
If linear elasticity doesn't apply, then Eshelby solution doesn't apply.
Correct.
And so I presume the assumption is that the deformation of whatever medium you're considering can be characterized. The elastic energy dominates.
Exactly.
Characterized by linear elasticity. That doesn't hold. Doesn't matter whether it's Eshelby or some other solution. It just doesn't hold.
But in the far field, it should always be right. Because in the far field, it should be linear.
Holds on all scales. That's the case. It still holds.
I mean, it's remarkable how well linear elasticity holds. I know of full atomistic solutions where core of a dislocation. Once you get beyond 8 or so atomic displacement, linear elasticity works well. Depends what questions you're asking.
It it's a question for you, for everybody. But I don't know a lot about HLB inclusion, but so here you have, let's say, unique HLB inclusion. You have this field, elastic response. When you have many HLB inclusions, you have do we know how it works? And at which level I can say that the sum of the elastic response of a medium to many inclusions will be the same as the sum.
Well, at the level.
As long as it's linear.
Yeah.
Yes,
No. You have
The medium is linear elastic.
each HLB inclusion will deform the elastic field. So
Yeah, but in the linear theory, the response is the sum. That's what linear theory is. The moment you have nonlinearity, it's no longer to be the case. In linear theory, it's by definition.
No, I agree with that it is, but there is one issue that was also raised in a question to Alan Nidelman, which is, in fact, when you have a shear transformation that is operating, it is not this inclusion when it is yielding is not elastic anymore. It's more like viscous. So if you have many of them, you can then you can question the fact that you're. But so this, if you use an elastic propagator, this is an issue. If you use finite elements by construction, you are taking this into account. I mean, this finite element here is not treated as an elastic medium, so and as an elastic element. So it's.
Sorry.
Ron was first, sorry.
I just wonder about the relation in this work and a lot of stuff that has been done in the 70s and 80s, like by Jean and Lalit Anand, about the role of dilatancy, so coupling between shear and dilation and its effect on the orientation of localization, and looks like the same idea.
Well, I would be happy to learn more about it, and I was hoping, in fact, but I mean, the new point that you do have a dependence on dilatancy that is here in the absence of friction. The new point that we are making with respect to that is that this angle is for the correlations and not for the shear bands, and that the angle for the correlations and for the shear bands are different, and they are different we haven't included the dilatancy for the shear band calculation that I showed, but we could do it, and probably we would recover this type of results in the case of a non-frictional system.
I think worth looking at soil mechanics and also plasticity. It's a lot of work.
I still want to raise some doubts about the pure applicability of the elasticity theory to granular frictional system. And we are running simulations, and you see there are all kinds of catastrophes. So you have those force chains, and they suddenly break in a new force chain arrangement, which is not at all actually measurable. And you have many frictional local events, rotation when you cross the yield limit locally, then Coulomb law. So I'm not sure that all the events can be put into this picture, and I think one has to think carefully. And I'm not sure that the simulations that you show that already take into account this formulation will be in full agreement with actually granular simulations with friction. I think one has to be careful with this.
I agree. So the simulations we do are on a very well specified model in order to test the assumptions that we are making. We are not claiming that they are reproducing the granular medium, but it's also because actually Hamon and Grassou they interpreted their experiments without using the idea of a local friction, and then everything was put into the dilation, which was far too large. So we tried to correct that. But I agree that.
Okay, last question by Michael.
So this may not be a question. I wanted to try to tie together, since we've had sort of 4 talks about amorphous plasticity, because I think there are relations between all these things, but I don't think necessarily it's so clear. And I think maybe touching back to Alan's model, like we have a model there that attempts to capture amorphous plasticity on this sort of mesoscale. And so ostensibly, like these other talks that are more on the atomistic or defect scale should inform these things. But I think there are sort of two questions being asked, and they're both necessary. It's necessary to answer both, right? Both, what is the instability that propagates across the system in, like the elementary event? And then how does the system get changed by that happening, right? So that Alan could answer, like after you've had something propagate across the system, how are the thresholds now different? How are the sites that are operable different? And, so I think both of these are important questions to ask. I mean, that's not really a question.
Okay.
An attempted solution.
Let's thank Jean-Louis